Today we will be building this soldering kit from, I got this from a friend of mine. It calls itself an LED chaser. It has a little instruction manual over here, and, all the various instructions of how you're supposed to put this thing together. It also comes with a schematic and a table of the components. And of course, all of the rest of the parts are inside this thing. So I'm going to put this thing together off camera, and then we can take a look at it and maybe even reverse engineer to see how it works. So here it is, nicely finished up. And now it's time to plug it in. This cable that comes with it goes from this small barrel connector to USB, so I can plug this side into the power input and then plug the other side into my $300 USB power supply. There you go. And now we can turn this thing on and revel in the experience. It's got some nice little flashing lights, right? And depending on what settings you have this on, you can change the speeds. Like, for example, this one is just all of the LEDs moving like that. And it's got a bunch of different cool little settings. I'd say this is the default setting. It just makes the LED move side to side like that. And of course, you can increase the speeds to get a kind of like a raster on a CRT TV, and eventually you can go fast enough so that it produces these sorts of stripes. And then you can set a bunch of different odd little modes. Another sort of raster style mode. That one's just moving the line across. A bunch of cool little settings. Yeah, it's kind of interesting to see how this thing works. However, I mean, the operation is nice and all, but how does the thing actually work? Well, at the heart of it, there are a couple of these chips. These 16-pin chips right here. Let's go ahead and zoom in on the label. CD4017BE. So these are, I think they're called decade counter chips. I'm not really sure what the proper name for these things are, but basically you input a clock signal and activate some of the inputs, and it just activates each one of its inputs one by one. And in fact, I think I can demonstrate one of these chips on a standalone board with a couple LEDs. Alright, so here I have built the CD4017BE into its own little basic circuit on a breadboard, and if you can see what's going on, oh man, I should probably remove this LED. This is the clock, by the way, so that all you can see is just the counter LEDs. I'm not really sure what's going on with these last two. I think those are special inputs because if it was only 8 inputs, that would be 8 bits, so that would be easy. But I'm not really sure what's going on with the last two, but you know what? We can forget about those. And you can see how it basically just counts up from, just scrolls along, counting up just like that. It's pretty simple, isn't it? And there are basically two of these chips over here, which are working together to turn on each of the various LEDs in this matrix. But how do LED matrices work? Well, we will take a look at that next. So, the purposes of LED matrices are it's to be able to light more LEDs with less pins. So here I have drawn a simple diagram of a 9x9 LED matrix, just what this thing uses. So, how would you turn on one of these LEDs? Well, let's say you wanted to turn on this LED over here. Well, what you would do is that you would activate this pin and you would activate this pin. So that would cause this LED to turn on. Maybe you want this LED turned on. You activate this pin, and you activate this pin. So this LED turns on. This allows for more LEDs to be easily controlled using only a couple inputs. So this right here is 18 inputs, but there are, I think, 81 LEDs in this matrix. Yeah, 9 times 9 is 81. So you can control an insane amount of LEDs using only a fraction of the pins that you would use. In a real-world situation, what you would probably do for this is have all the LED anodes wired up together in each one of these single lines. So each one of these terminals controls all of the anodes for a single row of LEDs, and have the cathodes for all of the LEDs be connected to to all these pins. So by bringing this one high and this one low, then you can turn on this LED. It's a very simple process, and it's probably what they also have done for this thing. But I'm not really sure how you would make a 3D LED matrix, because that would mean 3 pins for each LED, and I'm not really sure how that would work. But I know it does work because I think a lot of Great Scott's older videos would have shown a 3x3 LED matrix in the intro. But 3x3 LED matrices are possible, but I'm not exactly sure how they would work. But the 2-dimensional LED matrices, like in here, are pretty simple to use. And you might have also noticed that there are a lot of transistors around the edges. That is because these things might need to drive multiple LEDs at once, and these things do not like having more than about 50 milliamps of current drawn from their outputs. So you put transistors, which basically take the signal from the chip and amplify it so that you can draw like maybe 500 milliamps instead of 50 milliamps. And 500 milliamps is plenty to light up a couple of LEDs. Alright, so now that we know how each one of these counters work and how the LED matrices work, let's talk about some of the other things. The potentiometers are nothing really special, they just control the speed of each one of these oscillators, but these switches are kind of odd. So S2 over here, S3 and S4, those are the 3 switches that control the board. And so if I go over here and activate S2, it suddenly makes the x-axis go by a lot faster while the y-axis stays the same. For S3, it suddenly makes the y-axis go much faster, but the x-axis stays the same. And if I activate both of them, then you get this sort of effect that we were talking about with the other one. And oh man, look at that. Now we got the very slow and kind of nice looking thing. It's significantly less flickery just because it's going so fast, and the LEDs have actually dimmed a little bit because, I mean, they're flickering, but they are on a lot of the time. And if I just touch some of this stuff, it kind of sometimes makes it go a little bit faster. That's just how sensitive some of these resistances are. Like if I'm touching the bottom of the board, then I can kind of get some stuff to happen because, I mean, it's really that sensitive. It's kind of insane. But anyway, S2 and S3 basically just make the x-axis and y-axis go a lot faster, but then what does S4 do? It seems to just make it count up by each one of these. And I mean, that one makes the count a lot faster, but then this Y speed potentiometer is completely unaffected. So let's go ahead and go to the schematic to see what these switches do. All right, so here is, wait a minute. This, it's kind of confusing to look at. All right, so here's S2, S3, and S4. So as you can see, S2 alternates between two different values of capacitors. 220 nanofarad and 1 microfarad, same thing for both of them. It says 224 picofarad, but in reality this is written in the component marking format, so the third digit actually says the number of zeros, so that would be 220,000 picofarad or 220 nanofarad. And for a smaller capacitance, the oscillator runs faster, and it worked with both of those. So you could see how S2 and S3 could affect the speed. Meanwhile, S4 is a little bit different because it takes the, I guess this is the x-axis. It allows it to switch between the output of the y-axis, or maybe this is switch. This one might be the y-axis, this one might be the x-axis, but it allows you to switch between the output of the y-axis and the output of this little circuitry over here. So you could see that because if this is the normal speed, but here it is with S4 on, you can see that it is at that as it scrolls past, it increments every time that it overflows. So you can kind of see how that sort of works. And the y-axis potentiometer does not do anything in this setting because it's disconnected. So it's only affected by the x-axis potentiometer, which of course can make it go very fast. So I think that is finally enough rambling on about this cheap little Chinese LED chaser kit. I mean, it's more fascinating than you can think. It's quite fun to play around with, I have to say, just by turning up everything so fast that you can barely see what's going on. It's fascinating, isn't it?